Okay, so good morning everybody. Let's start with the second talk of the series. So today we will go through the following topics. We will see the whole facility, as an example, HIT, my facility where I'm working in detail. So we will go through from the ion sources up to the target. Then I want to have a short part about the aspects of the control system. For that, I can only say some words to that because it would be worse to give a talk on this singularly. But okay. And the last chapter for today is about the movable transfer lines, or as we say, gantries, and what are the concepts and the realizations. Okay, what are the design considerations for such a facility? First of all, the ion sources. We need long service periods, stable operation conditions, different ion species, from proton up to, like, let's say, carbon and oxygen. And we want to have fast switching between the ion sources, so the solution is to have two easier ion sources. We will come to that later. So the injectors should be very compact, efficient, and the application of established techniques so that it runs very smoothly. Okay, so the solution for that is an RFQ and an IH drift tube linac in our case. We will come to that. The circular accelerator brings us variable extraction energies as we need them. We can have beam accumulation there, and we can have multiple extractions. All this is needed. And at the end, we need a high energy beam transfer to the different target stations, to the treatment rooms, where we want to have a capacity of 1,000 patients per year. How to realize, as we will see, clearly is we have to look for the safety reasons. Therefore, we need a reliable spillboard system and, well, optimum dose application. Oh, sorry. Okay, this is what we thought for the principal design. The realization is shown here. So we have these ion sources over there, yellow marked, and the short injector, the synchrotron, the high energy beam transfer lines, the gantry, and the patient treatment rooms, 3 in our case. And what is not shown here, we have a place over here where we can do a quality assurance, and we have in before a beam dump. So this is, in my view, a very useful thing, because we can operate the whole machine, having opened all the rooms where preparations can be done, and we can operate the machine to the beam dump. Again, a short look to the parameters which I showed you yesterday. So we use 4 different ion species, or we want to do that. Protons and carbon are used daily. Oxygen ions, in the case of HIT, only for the experimental area in the moment. 255 energy steps are there for protons and carbon, and also, as I said, for oxygen. You see the ranges of energies. In our case, we want to have 6 focus steps at the end for the irradiation. Currently, we use 4 of them. So they are in the range of some millimeters up to 20 millimeters. And we want to have at the end 15 intensity steps. In the moment, it's only 10. So for protons in the order of 10 to 7, 10 to the 10 ions per second, and a factor of 10, 15, 20 lower for carbon. This is what the machine has to do altogether, without taking the beam target and gantry angle in account. This is around 90,000 combinations which have to be pre-commissioned in the control system, and you can have a knob and say, I want to have number 60,133, and then you get the beam that has, let's say, 200 MeV protons, focus 3 or something like that. Okay, this is how the injector looks like in our facility. As I mentioned, we have these two ECR ion sources. In our case, we have carbon in one source and generate after the analyzing magnet and after the spectrometer carbon 4+, so an A over Q of 3. And we changed over the years now also to A over Q for 2,3 for protons also. So we generate a H3 plus ion in the ECR ion source and bring that through the spectrometer through the LINAC. So the overall design parameters, I will go only into a few one. The injector length is about 30 meters. A over Q is normally 3. This is a design ion, but we can go also down to A over Q equals 2. But normally it's 3. Beam exit energy is about 7 MeV, 12% of the speed of light. And the operating frequency is 260 megahertz. This comes from a history of GSI where we had 27 and 180 megahertz, and now we go to 216 to shrink the size of the cavities. You will see that. Okay, we come to the other parameters step by step. Okay, let's start with the ion sources. These are commercial available ion sources from the company Pantechnik. These are permanent magnet ECR ion sources. They work on 14.5 gigahertz for the microwave, which is put to the plasma. And the plasma field is about 1 Tesla for the solenoid, and there's also 1 Tesla hexapole to form the field where the plasma chamber sits in, and where the electrons are accelerated, and they interact with the molecules and then form ions part by part. So what we got out is, as I said, 12 carbon 4+ and H3 plus for protons. So then we step now to the low energy beam transport. Clearly there are some tasks to bring the beam to the RFQ. Then the spectrometer is necessary to bring out the right ion species. A second point, or the third point, is the beam dilution. So as I said, we have to vary the intensity by a factor of 1,000 roughly, and this is done by this triplet here. We just defocus the beam to decrease the intensity, and then the entrance of the RFQ acts as a collimator. Clearly, there are also some beam losses here along the beam path. But we do that all at 8 keV, so there is no radiation problem or something like that. So we can do that. Okay, then we need the switching between the two ion sources. And clearly then we need, because we go to a cavity structures, we need a chopper to bring out a short beam pulse, as the ECR ion sources work DC. So we waste 99% of the beam along this beam path, but nevertheless this is a stable configuration, and the ECR ion sources run very smoothly. Well, and the last point which the Levitt has to do is to match the beam to the RFQ acceptance. So the next part is then the radio frequency quadrupole. This is a sketch of that. This is the cross-section, and this is somewhat of a 3D visualization of the form of the electrodes of the four. They have those sinusoidal structures. This was developed by Kapczynski and Teplakov in 1970. And as I may have already said, they consist of 4 electrodes, and the modulation is shifted by p½ between these electrodes. The E-field component has also that direction, and what comes out is that you can do some functions in one single structure. You can do beam focusing in both transverse planes because of the quadrupole structure. Then you have a bunching of the beam, which is necessary for the drift tube linac afterwards, and you accelerate the beam in that direction. In our case, the structure is only 1.4 meter long, and we come from 8 kV to 400 kV. So there is a field simulation by Microwave Studio. You can see clearly this quadrupole behavior, which changes with the RF. Okay. This is a 4-rod structure, very small diameter, very compact, as I said. Well, nevertheless, it took us a long time to bring it into a good operation scheme. And in the moment we working on a new version, because the first one which was built has some drawbacks, mechanical ones, and so I think we will have the new structure in by the end of next year, just to have a better transmission. Today we have only 30%, and 60 to 70% should be possible, and we will do that. Okay, the last part of the injector linac is a drift tube linac. Okay, sorry, this is in German, but it's a nice animation. Okay, this is particle source. These are the drift tubes, and it's shown here. There you have the gaps between the drift tubes where the acceleration takes place, and you can see these particles drift free, and these are accelerated in each gap. They get a kick and become quicker, and then at the end you have an accelerated beam. Clearly the Biederoth condition has to be fulfilled. No. Okay, so here you can see how it looks like. As you have seen the animation, clearly as the beam gets faster and faster, the gaps had to be longer and longer. So each of these 56 gaps has its own dimension. So also these drift tubes, everyone has another length, and all these have to be arranged in the right way and to be aligned. So this was also a long story for the prototype, not for the copies later on, which now work at GNAU and in the Siemens facilities, and later on also in MedAustron. Okay, as I said, the length is roughly 4 meters, also very slim version. The RF power which you need for that is pulse power for roughly a megawatt, which is a word, but nevertheless this is feasible to do in such a facility. Well, and the rest I can skip, I think about. The average field gradient is something between 5 and 6 megawatt per meter. Not bad for such a structure. Okay. Next part of the machine is now the medium energy beam transport. There are, again, a lot of parts, so clearly the transport to the synchrotron. We have built in the verification of the linac beam properties. This is done by adding here phase probes in the straight section of the medium energy beam transport line, and to measure the beam energy we can do that online, and it runs 24 hours a day to check if everything works fine. Then we need the charge separation behind target foil, stripper foil. We will come to that. Again, we have a second chopper here, which is a little bit of luxury, but we can then shape again a little bit the beam for the injection to the synchrotron. Well, and at the end we have also a debuncher to optimize the linac beam energy sharpness to the synchrotron injection. Well, okay, that's it. But so now we have to come to the final particles we want to have. This is protons. This is later on 4 helium-2 plus, carbon 6 plus, or in the case of oxygen, 16 oxygen 8 plus. Okay, for the hydrogen molecules, there is a task to break up the molecules and to strip away the electrons. Helium will be unchanged, will just cross the stripper foil, but for carbon we have to strip away 2 of the last electrons, and the same for oxygen. How does it look like? It's a ladder with targets on it. These are carbon targets, so the thickness is about, the foil material is about 100 microgram per centimeter squared. So the foil thickness is about half to a micrometer, very thin. You can look through them. The foil diameter is very small, so we have a waist here where the beam crosses the targets, and well, this works. And as you see, we have a ladder with 10 positions on it, because we had the impression at the time of designing that we should have the possibility to change them every month or every second or third month. But we work with the same foil since 3 years, and she is still good in a good shape. Okay. So then let's come to the synchrotron. These circular machines, as I already mentioned yesterday, were invented and developed after the Second World War. Synchrotron clearly is a machine of constant radius and variable B field, and also the frequency has to be variable. There is a synchronous ramping of the magnetic field in the higher frequency. Clearly, this is the name. And the particles perform Betatron oscillations around the orbit with this tune value Q, where the phase advance is divided by 2 pi. So how does it work? So we have an injection part, then we can bend around the beam 360 degrees, and we have only one acceleration gap to accelerate the beam, but it's done in each turn, and so we gain a lot of energy in a short time. So our synchrotron has a diameter of roughly 20 meters, circumference 65 meters. The magnetic rigidity is 1.1 to 6.5 Tesla meter. He has mentioned what it means, this magnetic rigidity, for people who are not familiar with that. The synchrotron is mainly occupied by 6 dipoles of 60 degrees, 12 quadrupoles for focusing, 4 sextupoles for the optics correction, and a lot of other systems which fill the gaps. What you see, the ring is really full, so we have less space for put in every other things, but we do not need them, I think, in the future. So for the injection, there are a lot of separate methods. So from single turn injection, where you only inflect by a fast kicker magnet the beam into the injection into the ring. There you would need a small emittance, and you have no beam accumulation. Then what you surely know here at CERN, one could use this stripping injection. This is mainly used for H-, and injected beam is P, the proton beam. This would not be feasible in our case, because we use also carbon ions and others. RF stacking is possible, and what we use in our case is multi-turn injection. So this is transverse stacking. What you need is a dynamic local closed perturbation, whether you use bumper magnets for that. You have a beam accumulation. Normally the factor is, in our case, about 10. But what you have at the end is a large horizontal emittance, and you need the right vacuum for that. How does it look like? You have to have a local orbit bump. This is done by this kicker or bumper magnets. And what you see is this transverse stacking process in the phase space. So you place the first in the middle, then you shift that in the x direction and in the xy direction. So this is done, and you have more or less a spiral behavior of this process. And at the end, this is what comes into the machine. It's a partly filled phase space, and here you can see the injected beam, and this is divided by the septum, by the electrostatic septum. Hopefully you can see this is the pulse in the middle energy beam transport area, and then you have this multi-turn injection, so you have a factor of 10 that you gain in beam current after this process. In the graph is shown what we use for that. These are the bumper magnets, 1, 2, 3, and the septum over here. So how do they look like? The bumper magnets are very fast, very compact steering magnets. More interesting is the septum, which is formed by one metal plate, and on the other side you have a harp of wires which you cannot see, but they are installed here. It's a harp with one tone because the wires are all the same length, and there are 300 in our case in the machine, which form the other side of this septum. Okay, let's come to the acceleration part. This is a two-step process. First of all, the bunches which came from the LINAC with a frequency of 260 megahertz, they vanish very fast after the injection process, so you have more or less a DC beam in the machine after some milliseconds. Then you have to do a RF capture, and we do that at the second harmonic, so of the frequency which the beam has turning around. In our case, this is about 1.8 microseconds, which the beam needs to go around. And well, therefore, when we go to the second harmonics, we have a working frequency at the injection of about a megahertz. And then you capture the beam, and afterwards you accelerate the beam to the desired end energy. The device used for that is a MA-loaded cavity, which we got from the supplier Hitachi. The maximum voltage is not very high, 2.5 kilovolt. But as I said, the energy gain is done in every turn. Okay, then at the last point in the synchrotron, we have to extract the beam. In principle, there are two different methods. So you can kick out the beam by a fast extraction. You do that if you want to transfer a beam from one machine to the other, to another machine, or to have special experiments. But this is not not our case. So what we have to do, we have to provide a DC beam, as I told you yesterday, and this is generated having an amplitude-dependent instability of the separatics. I will come to that. We have a tune shift close to the third order resonance to bring it out, and this resonance excitation can be done in the following way. So first you have to look, we have to go to a third order resonance to bring the beam in a shape that that the transverse Betatron oscillation gets bigger and bigger. But what you have to look for when you drive the machine, that you stay away from these dangerous low order resonances and just bring the beam to the third order resonance just before the extraction. And well, this is shown in the tune diagram which we use for carbon, helium, and proton. If you want to cross these dangerous low-order resonances, then you have to do it very fast. Okay, so for this slow extraction, you can do that in two different methods, or maybe there are some others, but these are the typical ones. The one possibility is to diminish the separatrix with optics. So there is a stable area and an unstable area around that, and you extract the beam along one side of the separatrix, and then you have the septum again for the extraction and bring out the beam by magnets. The other possibility is blowing up the emittance of the beam and to bring out, have a constant separatrix and bring out the beam from the stable area to the unstable by blowing, by knockout extraction, how we call that. And this is our method. The principle is not very complicated. You have a resonant excitation of the magnetron frequency with an RF exciter. So what you add on the electrodes is more or less a pink noise, a bandwidth of, let's say, some megahertz. And you can excite the particles and bring more and more particles to the larger Betatron amplitudes, and you can have the constant a constant separatrix. The advantage of that is you can have slow extractions from 100 milliseconds up to 10 seconds or even longer, but these are the typical numbers we use in our case. As I said, it's a big advantage to have a constant ion optics during the extraction. And what is also possible is to interrupt the extraction process, or spill interruption as we call that, so-called spill pauses. Why do we need that? If you think about one slice of a tumor, then it's not always the case that the area is only one area. It can be interrupted in several parts. So then you have to irradiate the first part of this slice. Then you have to interrupt the beam, virtually go with the beam to the next area you want to irradiate, switch on the beam, do that, and so on and so on. So this is normally used because tumors are not so compact that you always have constant area, only one area to irradiate. So this is a very often used feature. Okay, so as I said, we need a very good DC beam. And well, the first idea that was done is how can we come from a normal shape which has maybe a little bit sinusoidal, or it is a triangular shape or something like that. What you want to have is more or less a rectangular shape where you just have a DC beam with the noise which has a beam in itself due to the filling of the phase space. What we found out that we model the amplitude of the RF knockout exciter amplitude by an 8 energy dependent parameter setting. It looks normally like this. So you have to enlarge the amplitude at to the end of the extraction in a special shape. This works, but clearly, as the phase space is not filled always the same time, this varies still. But nevertheless, this is a shape we work together with. I will tell you what we're doing to make that better for the future and to adapt that tomorrow. This is a concept which is called dynamic intensity control. So we will go from forward driven values to a real control loop, but I will report on that tomorrow. Well, okay, I have mentioned already here. So the extraction devices are the following. We have the exciter, which has to be placed anywhere in the ring. In our case, it's directly in the injection area. You see here the last bending magnet of the middle energy beam transport area. These are only the two RF lines which go in the electrodes are inside. Then we have sextupoles for the correction of the orbit optics, and we have the septum which brings out the beam afterwards. Okay. Altogether, the current variation in time during the synchrotron look like the following. We have the multi-turn injection, as you have seen here. This is a scale of 500 microseconds, so it's very fast. The injection is only 40 microseconds, and then the beam stays more or less constant. No, after a short time, the RF capture and the acceleration starts. We have a little bit of a beam loss here, then we have the acceleration. This is more or less an artifact because at that point we change the optics, and the DCCT is directly nearby to a sextupole, and there's a little bit of influence. We sort of bringing out this problem, but the operators say, no, we can see that everything was working well. Please let it in the signal, and we have a good feeling that everything works well. So, okay, this is just not a current loss. This is an artifact of the field of the sextupole. Okay, you see the time which goes along. So altogether, one cycle is about 7.5 seconds, and then you have a gap for some control system things which we have to do. And so altogether, our cycles are in the order of 8 to 10 seconds. Okay, so when we have the beam out of the synchrotron, then we have the high energy beam transport area. You can see that we have 2 horizontal target stations, treatment rooms, then the gantry. Then I said here there is the beam dump, which by the way is a 30 ton of iron which we got from GSI, an old beam dump which was used there at an experiment. So what we have to do here is to bring the beam clearly to these target stations. We need the safety function to switch off the beam in case of an interlock from the target stations as fast as possible. I will come to that. We have to verify the beam properties of the extracted beam, and what we have to adapt is the beam width and position setting at the ISO center. These are the target station positions here. Okay, this is the so-called spill-aboard magnet or magnet chicane. So it's formed with 2 slow stereomagnets and 1 very fast. This is nothing else like a copy of the bumper magnets in the synchrotron. So normally the particles go this path, yellow and then green. They always make this bump, and in case of an emergency interlock, then this magnet is switched off and the beam goes to the scraper, which is located here. Everything to shut down the beam here is less than 50 microseconds. Okay, and then we use detectors for beam monitoring. Just a short look on that. We have feed-throughs which we can drive into the beam lines, which have a vacuum window of, this is consisting of 50 micron stainless steel, to bring in detectors which work with the gas, normal air pressure, but we use a mixture of argon and CO2 for the ionization chamber as well for the multi-wire proportional chamber grid. So what we can do at any station is to measure the intensity and the beam position and profiles. We drive them in regularly in the morning during the quality assurance, and in case anything is not going very well, this is very seldom, but normally all these detectors are clearly out because they cause straggling of the beam. Okay, What we have to do and to adapt is the different focus settings. As I have told you, we have 4 different focus settings in the moment. This has to be done first with simulations. We have a code from GSI who do that, and then we have to adapt the focus widths to all these different target locations. There is always a pair of quadrupoles just in front of the wobbling magnets for the scanning technique. What you can see here, these are pictures from March this year for the beam width and the beam position. We normally look that we have a band of, let's say, plus minus 10% from the desired value. We have to fulfill plus minus 25%. This is for the full width half maximum in the horizontal direction, and this is the position of the beam. Okay, 1 point is out. Okay, that is not so big a problem. Especially the focus is more a problem to keep it in, because this directly goes into the dose adaptation, whereas a little bit an error in the position can be corrected by the steering magnets of the scanner system. And this is the same story for the vertical values. Okay, and what is shown here is a little bit an older view of March 2009, before we started patient treatment. This is for the situation for 1 month, how it varies a little bit concerning the positions and the beam widths and beam focus width in horizontal and vertical plane over the months. So the machine, it lives a little bit, but the variations are very small, and so we can stay with our parameters for some months before we have to retune sometimes. Okay, so this was a story going from the ion source to the target stations. As I have mentioned, we have a lot of settings for the different beam energies, focus, intensities, and so on. So I want to mention a little bit the aspects of a control system which can do that. But in before, you have some conceptual design decisions to make for such a irradiation facility, because altogether at the end we have a medical product. And if you produce a medical product, then you have to fulfill this medical device directive. These are European rules, and there are more or less equal or similar things in the US FDA rules. And to fulfill them is a hard task. And therefore, we make an interface between the normal machine, which we have to qualify, certify as an in-house product, as a more or less normal CE level product. And then we have a dedicated interface to the irradiation technique around the patient, which is a medical product. I think this is a wise decision, because I just called our supplier some days before the talk and asked him, please tell me what is the work that you have to do if you make a software for a control system or a normal scientific technical software package and for a medical product. So he said to me that the effort is 50 to 100% higher for a medical software product for the first implementation, and especially if you want to have changes later on, then the effort is a factor of 3 larger than for a normal product, because you have to do all these regression tests, you have to do a lot of documentation and everything. So software for medical products are very cost intensive. So therefore, we have given out the contract for the control system to an automation supplier for the accelerated control system, and the medical product was done by Siemens, who is a certified medical product supplier. Okay, how does or how can a control system for a facility like HIT could look like. So we have decided to have only a two-level control system. So we have the real-time level here. There we have different devices for the power supplies, RF, and these devices. We really have developed a so-called DCU, an embedded controller. So for any power supply, we have such a controller with a large memory for all these different settings. In the case of the ramp magnets, there is also, we have only 255 energies times the ions, but then you have a lot of ramp data. In the other case, you have this lot of combinations of energies and focus and so on. Not for all elements, but for some of them. And especially for the devices where we come to the gantry, we have angle-dependent settings. So they need a big memory. So we have RAM memory for bringing and tuning the beam. And if we fix them and they are qualified by our medical physicists, then we bring these values to flash memory where they are stored and then they are safe. Okay, this is the real-time level which needs a real-time bus. So we have some main events in the machine which they now inject the beam, now start the extraction and so on. This is only a few commands which go along this real-time bus. Everything else is done by programmed delays. What we decided just from the beginning, because we had some bad experience at GSI, to embed the beam diagnostics directly here. This, in our case, we decided to have PXI crates, but they act more or less as the DCUs here. They have the same software structure and they are completely embedded. Okay, this was the starting version of 2006, and now, as you have seen here, we have replaced all these different machines in one blade server now. And the next step, which we want to do next year, is a complete virtualization of all processes, also of these gateway computers, to bring this on one blade center, to make it redundant and so on, to have a better performance of everything, which today is not bad, but we can do it better. So the heart of such a control system is clearly a database, in our case an Oracle database, for storing all the device parameters, all the devices which group a so-called virtual accelerator. So these are functional subgroups from the source to the target. The complete optical model for all the different parts and all the parameters are in this database. We have a lot of spline coefficients because we interpolate data. I will come to that later on. All the cycle data, all what is going on in the machine is stored there. So this is current values from the transformers. These are data from the power supplies. They all also measure values, ramp data. Everything goes to this database. And clearly we have alarm and error logs, the user access rights and everything else is stored there. This is the heart. And a lot of reports can then be derived afterwards in case of failures. We can do error analysis just days afterwards because we store these data for a long time. But we can also do a lot of beam statistics from performance of how and where the beam requests are, and so on and so on. So this is a worthwhile thing to see. And just one example is we automatically produce reports every day where we show the statistics, how many cycles were done, how many cycles had problems. So this is in the order of 1%, where we can see that there's a problem was reported. And not in any case there is a problem with the beam, but there may be a short deviation of a single device, and everything can be seen from such a database. This is a long story. So, oh yeah, good in time. So the last chapter of today is gantries. Well, we have seen the whole machine and the high energy beam transport area, and the horizontal rooms is just a straight line to the isocenter. But what is the motivation to bring the beam from different sides into the patient? I have only one example here. These are pancreas tumors. People who are a little bit familiar with this topic know that they are very, very dangerous and can lead to death within weeks and months. The problem is that they have a very delicate position. So if you want to go with beam directly to this position, then you would cross the spinal cord, which is not a good idea. Then you have other organs which you would have. There's only a very, very, very near channel, a small channel where you can go to such a tumor. And clearly, as anyone is an individual, you need individual irradiation angles for such patients. And well, this is one motivation, not only the only one. To have an angle-dependent beam to the patient. Gantry geometries were thought of a lot of. It started with these so-called corkscrew gantries in Loma Linda. We have seen the facility yesterday. Then there were compact gantries, like the first one at PSI, an eccentric version. Then we have the version that IBA developed for their facilities, the first one in Boston. And there are a lot of other geometries which you can think of. The central question is always, do I have an isocentric gantry? The patient is fixed and the gantry bends around, or do I choose an eccentric version of the geometry? Examples are the PSI-1 gantry and the so-called Riesenrad iron gantry, which was a study within the PIMP study. So, but the choice is, in my view, this is my personal view, is really simple. When we ask the medical people what to do, when the HIT project started, they say the patient is in the focus, the technique should grope around. And medical personnel is used these isocentric gantries from photon therapy. I showed this picture yesterday. So they said no eccentric version again. And this is just a feeling from the medical persons. Clearly, they have experiences well, they are the customers. We have to fulfill their wishes. But I think there are some additional arguments, especially safety reasons, to go to isocentric gantries. And I want to tell you only one. So if the patient who is fixed in a mask has a problem with respiratory or with vomiting, so then you have to go to him within 20 to 30 seconds. And well, as you know, such a treatment room is a fixed room. You have to open the door. Sometimes it's a bigger door for radiation safety in our case, or you have a long floor to cross or something. So 20 to 30 seconds is really a hard task. And if you then would have an eccentric gantry where you have to cross 2 or 3 levels to come to the patients, in my mind, it wouldn't fit. So, okay. And again, this picture, the different versions, but nevertheless, most of the gantries worldwide are of this shape, and I think it's not, it was a development also at PSI, who made a lot of experiences with gantries. The first gantry was an eccentric one, the second one they built is an isocentric gantry now. So we can see here some examples. from commercial companies. So this is the Mitsubishi version, which forms more like a tube with the beam bended around here. There's also some magnets, or the IBA version, which is more a structure version of that. Nevertheless, they have all a very large bending magnet at the end with a large bending angle of mostly 90 degrees, but also with 135 degrees at the end to bend down the beam to the patient. And well, this is to be seen the gantry 2 of PSI. This was during the installation, and this installation is now finished and commissioning is underway. They have the bending angle of 210 degrees, not fully rotatable, but okay, this is to neglect. What you have to choose is if you want to use scanning, where to place the scanners. You can do that after the last dipole. This is the normal, or I would say the most implementation you find, most implemented version you find for proton gantries, to place the scanner magnets just after the last bending dipole, because it's possible with the 2.2 Tesla meter rigidity of the beam maximum to bring out the beam here to an area of 20 by 20 centimeters. But okay, this brings a larger diameter of the gantry. You need a larger room. This goes into the costs and so on. If you do an upstream scanner, then you need a large diameter of the last dipole, and this makes it very heavy. And this goes also into cost. So it's not easy to make this decision for protons, but for ions it's clear this was never fit, so we would have a gantry with a diameter of 20 meters or more to bring out here the beam afterwards. So we have to decide for such a situation. And you have to think about a lot of other things. At the end, you have to bring the vacuum as close as possible to the nozzle because of the straggling, and the nozzle as close as possible to the patient, to the target volume, but nevertheless you have some safety rules so you are not free in any parameter. So it's a long process to develop all these right dimensions. And this is our solution for that. I've already shown that. So we have two 45-degree bending magnets and a 90-degree dipole at the end. The treatment room is inside the gantry structure. The patient is in a fixed position. It's an isocentric one. And, well, this is a picture of that. What you clearly have to fill is the position accuracy for quadrupoles, which is plus minus a half millimeter. You have a structure with a radius of 13 meters and 25 meters long. This is not an easy task, but the company which did the job normally builds radio telescopes, and they are much larger and have to fulfill same accuracies within a half or 1 millimeter. So they are used to move big things with a high precision, and this works perfectly. Okay, the gantry setting, the optics for that is a delicate thing. So we have done that in the last 2 years and the last months intensely. So clearly you want to have a full transmission, so the better functions have to stay within the limits. We have basic settings for all angles, keeping the variation of beam focus and width independent, firstly, of the gantry angle. But then you have compensate effects of coupling the horizontal and vertical phase space. You have not the same emittance from the synchrotron in both planes, so you have to adapt that. and the beam size adjustment has to be done also with the last quadrupole doublet in our case. And what you see is you can stay within the band that we have also for the horizontal rooms. So full width of maximum in this case of about 10 millimeters with plus minus 25% deviation possible. But still you see a little bit the sinusoidal structure for the deviations, which is hard to bring it really to a minimum. But nevertheless, this is the result. We can have the same beam sizes as at the horizontal places. We measure that with a scintillating screen target here, which is fixed to the nozzle for this tuning in the machine, where we can see in 2 dimensions the beam. And then we find energy and angle dependent settings for the focusing quadrupoles. And well, we cannot do that for any angle, so the values are stored for 36 angles, so every 10 degrees. So we normally tune in the machine for 4 angles or 8 angles. The rest is done by spline interpolation over the base points, and then you get this fit curves. And well, what comes out? So this is an example for carbon at 190 MeV and 400 MeV proton beams, and you can see that we can stand and fulfill the limits. And but it was a hard task for my colleagues who have done the job always in nights, because as a day over, we irradiate patients. So at the end, we have now the beam size within the accepted deviations. Beam position stands within plus minus 2 millimeters. The rest, as I said, correction is done by the control loop of the scanning system. And what we have now is a very good stability and reproducibility. So for the proton beam, we have now a fixed situation since some weeks, and we find that it's very stable once you have run that in. Okay, as I said, residual position deviations are done by the fast position feedback of the scanning system. It's now suitable for the patient treatment. And you can see the big machine rotating in this small video, so outside and inside. Okay, this was at the time where not all of the devices were fixed in. Well, you can compare now the size of such gantries, and well, it's a story. This is the PSI gantry 2, 12 meters long, 8 meters in diameter, and we are much larger, and the weight scales by a factor of 3. So this is clearly not the end of the development, and I will show you tomorrow what is going on there. Especially clearly we have all normal conducting magnets, and I think we will switch, or one will switch in future to superconducting ones. But this is a delicate story. I will come to that tomorrow. But nevertheless, it's the first worldwide ion gantry, and it will irradiate patients starting now in October. And well, we will see what are the outcomes for the patients and for the tumor treatments. Okay, just in time. A view to the talk tomorrow, and the last one. There I will go to all the daily operations of such a particle therapy center. I will tell you about experiences from the first 5 years at HIT, what we have done in Heidelberg to come now into a regular operation of all the 3 treatment places. We have started with some patients per day. Now we are at 45 to 50 patients per day, so 1,000 patients were treated so far. I will tell you a little bit about the story, what we have done for that. Then I will tell you something about the future enhancement for such a synchrotron-driven facility, what we can do there. And at the end, I want to show you some new concepts, what is discussed and developed and what is underway now. where are the ideas, and to comment a little bit on that, what we will see in the next, let's say, 10 or 20 years. Okay, just in time, 1 hour. Okay.
Are there questions on this?
I have a question about the rotating gantry. Do you need to set the beam angle very precisely, or could you imagine working with a number of fixed beam lines at different angles?
This is always a good question, but when you think back to the example which I showed to you, where we have very short, very small entrance channel for the beam to a pancreas tumor, for instance. It's not a chance to have then 3 rooms with 30, 60, and 90 degrees. This does not fulfill it because the patient you cannot rotate a little bit, let's say 5 to 10 degrees roughly. But also this is not easy. Everything which is weak in your body, to fix that and to have a position accuracy of, let's say, 0.5 millimeter, this is a story. It's not easy to do that. So, and the easiest way is to say the patient is in the middle. We position him always the same story, always horizontal, and then let's do the machine around the rest. So this is the thinking of the doctors, and I think from the customer view, this is not wrong. So they don't care about a large structure. They are in the patient treatment room. They do not see that. They know it, but they do not see that really, that this is a large machine behind the wall. So therefore, you need really a gantry which can have an angle. It must not be 360 degrees, so you can also rotate the patient table so then you can save 1/2 of these angles. But okay, in our case, it makes no sense to shrink the size from 360 degrees to 180. But in other cases, like in the PSI gantry 2, it makes sense to do that, to save in mechanics and costs. Okay, that was a question over there.
If I'm not mistaken, the Loma Linda gantry, because we're the first one ever built.
Yeah.
In spite of 360 degrees rotation, it is shorter than all the others we were built afterwards, it's slightly bigger, is only 90 pounds versus 200 pounds. Mm-hmm. Do you have an idea why it was never replicated? Because everybody else went for the other solution.
That's a good question. I do not really have a question for that, but I estimate some problems which may occur. So a little bit the same story is at Boston, where you have the last bending magnet which has 135 degrees. So a very long magnet, only a dipole magnet. So I think they will have problems with the beam optics. It's not easy to bring in the beam over such a long beam path without having quadrupoles to again focus the beam. This is one story. The second story is the stability and mechanical stability of such long, small and long things. Yeah? So we have seen, I go back to the Linac, the IH drift tube Linac is very slim. It's only 40 centimeters in square and 4 meters long. So such structures tend to be weak and to stay not within 50 micron or something like that. Okay, as a gantry you may have to fulfill, let's say, 0.5 millimeter. So I think it's mechanical stability, which is a topic. And at the last point, maybe a problem. If you have very long magnets, you have also the problems with eddy currents. So I don't know how long is the time switching from one magnet, from one energy to the other, from one field to the other. This may also be a problem. I don't know it exactly for the Loma Linda version, but I think this could be the reasons. It's always astonishing that this first machine installation of a proton synchrotron with everything around it was never copied. Yeah.
They're treated
Yeah.
So many pages.
I never understand that the company behind that, this is Optivus, never get a second chance to copy this machine.
I think it was Site, the company that did.
Now it's Optivus. Now it's Optivus. They do the operation and maintenance on the further.
Started with pure process scatter, so then you can imagine you don't need such a facility. So I also think that there's some mechanical rigidity problem. But now I think they went to process scatter.
Yeah. So, but to adapt that later on in such a gantry to adapt these scanning magnets, this was done in Boston, also a facility which started with simply scattering the beam, and now they have done, and this is a nice story, IBA itself developed a scanning system which should start the first runs in Essen in Germany. But it's not in operation until today. I don't know why. But Boston made an own scanning system, which is under operation now. But Jay Flans, the guy who is so the machine man at Boston, he told it was a very long story to bring it into operation because of the complicated optics in before. Okay. Yeah.
You mentioned that in the focus of the gantry there may be position errors up to 2 millimeters.
For the dipoles. For the dipoles it's possible because if they move a little bit around, you have a large diameter.
Due to deformation?
Yes.
And the second part of the question is, how does